welcome to this lesson. So, in this lesson, we're going to be discussing about work, energy, and power. Now, first of all, we're going to discuss the three principles behind the work, energy, and power, which are asked in the examination. So, when they are asked, the question is like use the energy principles to calculate whatever that you're asked to calculate. Now, I'm going to help you to be able to use those principles or these principles to your advantage. The first one is the work energy theorem, which states that the total work done on an object is equal to a change in the kinetic energy of the object, which is just work net is equal to total change in EK. That's what it means. This is the first principle that you should know, the work energy theorem. But on the work energy theorem, you are sometimes told that use the work energy theorem to calculate the velocity or to calculate whatever that you're going to be asked to calculate. Now, the second one, it's the conservation of mechanical energy, which states that the total mechanical energy of an isolated system remains constant. The total mechanical energy of the system initially should be equal to finally. Now, this one you only use it whenever the mechanical energy initially is equal to the mechanical energy finally. That's when you are to use this principle. Now, we know that mechanical energy is the sum of potential energy and kinetic energy. This is kinetic, this is K. That's how you go about it. Now, let's go to the third one. The third one, it's the non-conservative force principle. So the non-conservative force, it is only used when it's only used when there is or a non-conservative force or forces. That's when you are to use this one, which can also be represented by work done by non-conservative forces is equal to changing EP plus changing EK. So this one you only use it when you have non-conservative forces. That's when you only, and non-conservative forces, the examples are friction, tension, and so on. But if you don't have friction or tension or any of the non-conservative forces, you are not supposed to use this principle. Now let's talk about positive, negative, and zero work done. Now, before we go to a positive, negative, and zero work, let's discuss the formula that we use to calculate the work done for a certain force. So, to calculate the work done for a certain force, its work is equal to the force multiplied by the displacement and cos theta. So the F, it's the force, it's the magnitude of the force. Then the delta X, it's the displacement. Then cos theta, the theta, it's the degree or the angle. No, it's not the degree. The theta is the angle that is between the force and the displacement. Let me say it again. It's the angle between the force and the displacement. So let's go to our positive, negative, and zero work. So any force vertical to a displacement does zero work. And what could be an example of that? Normal force, e.g. normal force. Normal force always does zero work. That's why most of our calculations we don't include it, because it does zero work, since it's vertical to it acts vertical to the displacement. Now, any force that is in the motion of the opposition of the object's motion, it does negative work. What could be an example of that? What could be if it's not our famous friction force? So friction force, it always does negative work because it acts in the opposite of the motion. Are we together? It always acts in the opposite of the motion of the object. So that's why it does a negative work, because it makes the object to lose energy while in its motion. Friction. Now, any force that contributes to an object's motion does positive work. Any object that contributes to an object's motion does positive work. What could be an example? An example of that force that contributes to an object's motion can be an applied force. It can be an applied force, but not always, not all the time. The applied force sometimes acts in the direction of the motion. So if a force acts in the direction of the motion, that means that the force is doing positive work, since it's contributing to the object's motion. So now let's do an example so that we can apply all that we did. So an example: a groundsman pulls a 100 kg across a cricket pitch with a force of 500 newtons at an angle of 30 degrees to the horizontal as shown in the diagram. The roller experiences a frictional force of 250 newtons as it moves 25 meters along the pitch. So we are given the mass of the groundsman. We are also given the force. This is the force applied, since it's the groundsman that is pulling. It's applying a certain force to the roller. So it's 500 newtons, then an angle of 30 degrees, then the roller experiences a frictional force of 250 newtons. As it moves, we have our displacement also. Now there's our little diagram I tried to draw, as you can see. Yes, so there's a mistake. It's not 380, that's 250 newtons. Sorry about that. So our first question prompts us to calculate the work done by the applied force. The work done on the roller, the work done on the roller by the applied force. So by looking at the diagram, scrutinizing the whole diagram, we can see that the angle that we have here, the 30, it's the angle between this displacement and the force, which is the applied force. We can just use our equation. So this is the applied force multiplied by delta x cos theta. Let's substitute the applied force. We have it's 500. We have the displacement here, it's 25, and cos the angle between the displacement and the force, it's 80. Now if you punch correctly, you are supposed to get 10825,32 joules. So that is the work done by the applied force. So now we are asked to calculate the work done by friction on the ruler. So we were told that friction is present in our scenario. So we should have expected that question, and it's here now. So to calculate, we already know our angle, which is 180, because friction acts opposite to the motion of the ruler. Now, do we have the magnitude of the frictional force? Yes, we do. It's 250. It's this one we are given, so we can just use this one. There's a difference between this one and that one. That's a capital letter F, and this one is a small letter that represents friction. (250) displacement, that's 25, cos 180. And always, you know that cos 180, it's -1, so we should expect a negative answer. If you get a positive one, make sure you check your calculations or your substitution. Joules. That's a -6,250. So on our third question, we are asked that how much work is done by the gravitational force on the ruler, and we should explain our answer after that. So what do you think should be the answer? For not what you think, you have to know what your answer is. How much work is done by the gravitational force? So if we can check the gravitational force, the angle between the gravitational force and the displacement, it's 90 degrees. So we already know that cos 90, that will give us negative, not negative, that will give us 0 work. So we can conclude that the work done by Fg will be 0 joules, because, and the reason will be that it is acting, it is perpendicular to the displacement. Sorry for the background noise. I'm in my village. So now we are asked to calculate the net work done on the ruler. So since we discussed about our energy principles, what do you think should be the appropriate one to use here? The answer to that, it's none. It's none, because we don't have much to do, or we don't have much to use to calculate the net work done. If we were to focus on the first one, it requires us to have the change in EK, which means that we have to have the final velocity and the initial velocity, and we do not have that. So we can just add all those work done by the forces that are acting on the ruler. And we already know that the forces that are acting on the ruler is the applied force, the friction, and the gravitational force. We can't talk about the normal force, because we already know that normal force, it does 0 work. It does 0 work. So we can just write work net is equal to, we add all those that are acting, which is the applied force, the friction, and the gravitational force. So we already calculated the work done by the applied force, which was 10825,32 plus minus 625, and we did we calculate this one? Yes, it was 0. It's the one that we got on 1.3. So now you just add so if you multiply the positive by the negative, you will get a negative. So you just subtract 10825,32 minus 6250, and you will get 4575,32 joules. Then we are done. We just got our work net. Thank you for tuning in, guys. If there's anything, any problem that you have regarding work energy theorem or any topics that we did before, just hit us on the comment section and we will reply. Otherwise, please take care. Oh, and please, guys, do not forget to like, comment, and subscribe. Lots of love.